Good morning. All right, guys, today we're doing lesson number 7, which is on what are called vector spaces. We will have our normal kind of tutoring check-in day tomorrow, and then another lesson on Friday. Tomorrow, problem set number 2 is due, so make sure you guys have that on your radar as something coming up due. And then next week, problem set 3 will be due. And then the following week will be our test at the beginning of I think Tuesday of the following week. And that means Monday will be your 4th problem set that has 2 lessons worth of problems on it. So kind of like a normal time that's kind of coming up as well. Which means we're kind of getting near what we call the complete solution to AX equals B, which is kind of picturing no matter what we're looking at, how do we kind of give you a complete idea of what types of solutions we have to that? Okay, we put a lot of building blocks in place. We haven't really done much actual solving, but that's what a lot of these last sections are for. This one is pretty conceptual. Vector spaces are a big topic in upper level math in general. So some of what we do today wouldn't necessarily directly apply to linear algebra. At the end, we'll do one of the ways it applies to us. But really, it's a much more general, broad idea of vector spaces. And so it's not going to be a lot of concrete stuff like doing stuff with numbers. Okay, not even numbers in a vector or a matrix. It's going to be a really kind of general level of understanding. Vector spaces involve like generalizing patterns and things like that. So it may seem a little weird at first because you're not like adding or multiplying or solving something. It's more talking about what patterns do we see here and will these patterns hold. Vector spaces, the concept is used in proofs and things. So we're going to talk some about it. And then at the end, we'll start adding in like, where does this apply to what we're doing now? And we'll keep adding on to that in the next couple lessons of this idea of spaces. So you're already familiar with some vector spaces. So like R1, R2, R3, R4, those are spaces that consist of all the vectors with however many components. So like R1 would be any vector that has one component. So like the number line would be R1. Okay, you might have the number 1 or the number 2 or the number 2.7 or whatever. They're real numbers. Okay, R2 is the XY plane. It's all vectors that have two components. R3 is 3D space. It consists of all the vectors that have three components in them. So like R5 would be all column vectors that have 5 components. It's basically describing 5-dimensional space. So it's saying any vector that would have 1, 2, 3, 4, 5 components. 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. 1, 2, 3, 4, 5. Whatever you want to put in there, it's all the vectors with 5 components. So we've technically already seen a lot of these types of spaces. We just haven't talked about them in terms of them being a vector space. But these are just the space of real numbers. 1 real number, 2, okay, think of 2 like 2-dimensional space. R3 would be 3-dimensional space, and so on with real numbers. Okay, the components are real numbers, which is why we call it R. If you want other things like complex numbers, you would use a C for complex. So you could do C1, C2, C3, C4, and it would be the same idea, only you could include complex numbers. Okay, you could do integers only, which is usually indicated with a Z. Okay, and usually that kind of boldness, it's not a vector. If you see it written, it's usually like another bar. So like R or C will have like a bar here. Typically that's what you'd see like handwritten, is it's got another bar there. Rational numbers are usually indicated with a Q. Okay, so if you don't want all real numbers, but you want only the rational numbers, you would put a Q. And I think Q and Z come from other languages that probably means something to do with integers and I think the Z is definitely, I think, from German. I don't know where the Q comes from, but those are typical letters that you would say we only want to include integers. Okay, not all real numbers, just integers or just rational numbers or whatever. Okay, and the N would just stand for how many are in the vectors that we're talking about. All right, so R1, this is the one you guys have seen for the longest. It's visually represented by an axis, okay, the number line. So think like, I don't even know. Early elementary school, you probably start like drawing a number line. And you put 0 on the number line. And if you have, literally the vector will be of the form a number. Okay, so for example, 3. Well, then that would be visually represented by the vector from the origin, whatever you want to call that, to the number 3. 1, 2, 3. So it would be just vectors going along that line out from the origin. So it's a vector from 0 to wherever you put A. Okay, so they'd be parallel, right? There'd only be kind of one direction or the opposite direction that you could be going. So R1 would be basically, you can think of like the x-axis or a number line, just an axis. Okay, and your vectors would then just be lines, segments on that axis, basically. Okay, R2 is also one you should be very familiar with. This is the XY plane. Okay, so R2, if we have the XY plane, each vector is of the form, A, B, or whatever. AI plus BJ, or however you want to think of that. So for example, we could have 1, -2. And so your vectors would be, again, going from the origin. We would have something like 1, -2. So we would draw them as vectors from 0, 0 to wherever you're saying A, B. Whoops, this should really be. Think of those as points. So picture we could fill up this whole space, right, with vectors going out from the origin to whatever points, really far, really close, whatever. You could fill that whole thing in with those vectors going to any point on the XY plane, right? We could basically pick any point we want, draw a vector there, and we could fill in the whole space. Okay, R3 is represented by 3D space. We have less familiarity with this, this is a lot of what we did last semester is talk about 3D space. You have a little bit in geometry where you talk about 3D space. So you'd have your 3D space. You could pick any point in space. So any vector would be of the form A, B, C. So we might have 1, 2, 3 or whatever. So 1, 2, 3 would point out at this point, 1, 2, 3. Or I meant 1 in the X direction, 2 in the Y direction, and then 3 in the Z direction. And that's probably where visual representations end for us. But the same pattern would continue R4, R5, R6, R7, whatever. It would basically represent vectors from 0, 0, 0, 0, 0, 0, 0, 0 to A, B, C, D, E, F, G, whatever, however many numbers there are. We think of them as those vectors going there and covering whatever that space looks like. Again, visually, probably R3 is the last one that would really make sense to think of visually. Okay, so for example, 401 would be an R3, 11011 would be an R5. Once we get past probably 3-ish, a lot of times you might see them written in a line as opposed to trying to write a column that's going like this. They're still thought of as column vectors. So when we're doing all this stuff, think of them as columns, even if you write it as a row, because again, we're going to be interacting these things with matrices generally in AX equals B or whatever. This needs to be a column in order for that multiplication to make sense. So as we're talking about these, even if we start writing them kind of going across, we're talking about columns. It's just hard to write large columns up and down. That's not really the way the English language works very well or anything that kind of lays out well. So typically it starts getting to where you'll write them across. Still think of them as a column. All right, so the main operations that every vector space has, the two essential operations, are adding two vectors from the same space or multiplying by a scalar. Okay, lots of vector spaces have other things you could do, right? We have cross products and dot products in certain vector spaces or whatever. We have other operations too. These would be your essential operations. They're defined by kind of how it works in the space. So when we think our normal R1, R2, R3, R4, R5, R6 vector spaces, we know what addition looks like. Okay, but there's other things than just these, and we'll look at some examples in a little bit that are also considered vector spaces where they might say this is how you add in this space. Okay, it's just like when we had to learn how to take a cross product, or even back in first grade or whenever you learn how to add. Someone had to kind of show you, well, certain vector spaces, it might be this is what addition looks like. So just be aware, it's not always what you're thinking. So you'll have problems in your homework that's this is how you add in this particular space. Mostly that's just to kind of get you to think about what this would look like. Okay, but we have these two operations, addition, multiplication. I feel there's a time in elementary school where you do this fake operations where you circle it and they have you think about what that means. It's a similar idea here. Okay, and then whenever you see something that says it's inside the vector space, we mean the result is still in that same space. Okay, so like if I add two two-dimensional vectors, I'll get another two-dimensional vector. Okay, I won't all of a sudden get something three-dimensional or five-dimensional. If I take a two-dimensional vector and I multiply by a scalar, I will get another two-dimensional vector. Okay, so when we say inside the vector space, we mean that the result doesn't all of a sudden give you a vector that's not in the same space as the first ones were. And that's going to be a really important idea. That's what makes a vector space a vector space. Okay, that's what makes it have a predictable pattern of behavior, is that when I do these operations, I'm not all of a sudden going to get something totally different. If I add some real numbers, I'll get another real number here. Okay, so we have 8 main rules that must apply in order for you to be in a vector space. So again, it's just a way to categorize vectors that have something in common and follow a certain known set of rules. Okay, there are other spaces than just the vectors of real numbers. And again, we'll look at some examples of those in a second. To kind of identify if it's a valid vector space, which is most of what the homework from this section is. It's like, okay, what if we take these things? Does this make a vector space? Meaning, will this follow the rules that we're going to lay out in the rest of this course? Okay, it's going to meet 8 qualifications. The first 4 are here and the next ones are on the next page. 1, it should be addition should be commutative. However addition is defined in that space, it should be commutative. 2, addition should also be associative. So if you're adding a bunch of things together, it shouldn't matter how you group it. 3, there should be an additive inverse. Okay, meaning there should be a vector that behaves like a 0 in addition. And depending on how addition works, it's not necessarily just zeros. It's like we've seen the identity matrix. It's not a 1, okay? It's a bunch of 1s and 0s. So it's not that the 0 vector will be 0, 0, 0, 0, 0. It's that I have some vector that when I add it to another one, nothing changes. Okay, whatever addition looks like in my space, I'll have something that I can add and nothing changes. Okay, something that behaves like the 0 vector. For most things, it is literally a bunch of zeros, but it kind of depends on what addition looks like. There also should be an additive inverse, meaning some vector that I can add to get the 0 vector. Okay, this referring to whatever this thing was. Okay, whatever I got in number 3, there should be some vector that I can add to other vectors to get that same thing. And those are the main ones with addition. Commutative, associative, there should be something that acts like 0 under addition, and something that acts like basically a negative of my vector, that when I add it to my vector, I get 0. Okay, with multiplication, and again, we're talking scalar multiplication. There should be, when I multiply by the real number 1, it should not change the vector. Okay, 1 times a vector should equal that same vector. Talking scalar number 1 here, literally real number 1. For any 2 scalars, if I'm multiplying them times a vector, I could either multiply them together, then times the vector, or I could individually multiply them times the vector, and that should be the same either way. Okay, it's basically associative there, but with scalar multiplication. So either I can multiply them individually one at a time times the vector, or I could multiply them all together, then multiply by the vector. Should not change the result. For 7, that's basically the distributive property should work with addition. So if I have a scalar times the sum of 2 vectors, it should be the same as the scalar times the vectors added together. And then another distributive property, but this time with adding the scalars. If I add 2 scalars, then multiply, it's the same as multiplying them, then adding them. And so those are your main properties. And so there'll be several problems in your homework that are like, go through these 8 properties. Do any of them not work if this is what your vector space looks like? So we'll do some examples, but again, the homework will kind of have stuff where it's just kind of inventing an idea. It's just trying to make you think about it. It's not actually going to apply to what we're doing in this course. It's trying to get you to think about what all this stuff means. Most of what we'll see are pretty obvious vector spaces in the rest of linear algebra. So basically, however, addition and scalar multiplication by real numbers. Okay, when we talk about scalar addition, those C's in those last four properties, they're real numbers. Okay, is defined in the vector space. However, they're defined. When you perform them, you'll get other vectors also in that space. So if I take R2, and I were to think here, if I took two vectors in R2 and I added them, the order I added them in wouldn't matter. Okay, 1 and 2 would be fine. In R2, the zero vector is literally 0, 0. Okay, if I take the vector 0, 0 and add it to any other two-dimensional vector, nothing will change. Okay, for number 4, if I have a number like AB, a vector AB, I could add the vector negative A, negative B to it and get 0, 0. Okay, if I took 1 times any two-dimensional vector, I will get that same two-dimensional vector. If I took numbers like 2 and 3, multiplied them to get 6, then multiplied them by a two-dimensional vector, it would be the same as taking that vector, multiplying by 3, then multiplying by 2. Okay, that's all that you're doing when you're trying to verify is you think through these 8 properties and like, is there any way I could get something weird to happen if I'm taking two-dimensional vectors or whatever? All right, so R2, I kind of just went through those. You would basically want to say, so let's say we have a vector U, it's U1, U2, and we had a vector V, that's V1, V2, and we have a vector W, it's W1, W2. Okay, you want to think really general. Don't use just a specific example. Although, if you're looking for something not to work, all you need is one counterexample. Say, no, it doesn't work when I use these numbers or whatever. But if you're trying to kind of prove or show it, think generally, like with variables or whatever. So you would literally kind of go through and say, what would I get when I do U plus V? I get U1 plus V1, U2 plus V2. Well, what would happen if I did V plus U? U. I would get the same thing. Okay, and then 2, what would happen if I did U plus V plus W in this order? And then what would happen if I did U plus V plus W in this order? And show that they'd be the same. Okay, and you would just kind of go through the 8 properties and just make sure that they all work. They should all work in things like R2 and R3 and stuff with like normal addition, normal scalar multiplication. That's all you'd be doing is kind of going through and making sure that they all are true. Okay, vector spaces don't mean literal vectors as we're used to seeing. Anything can be thought of as a vector, and there are certain people that really think you should be basically using vectors from elementary school to teach all of math, because everything can be thought of literally as kind of a vector space. Most of what you guys do growing up can be. So like we could think of matrices as a vector space. Okay, so all real 2x2 matrices. So basically, any matrix that looks like this, A, B, C, D. You'd want to think, let's say this is A. Let's say B is E, F, G, H, or whatever. You would want to think, is there any way that AB does not equal A plus B, sorry, does not equal B plus A? Okay, could you think of any time that a 2x2 matrix added to another 2x2 matrix in one order would not be the same as the other? Okay, and if you add them together, you would get A plus E as your first spot, and then B plus F, and then C plus G, and then D plus H, and it wouldn't matter the order. Okay, and then you would want to do the same thing with the third one. And just make sure if I added them in different orders, it wouldn't matter. Okay, for 3, our 0 vector would literally be 0, 0, 0, 0, which is a 2x2 matrix filled with real numbers. This gives us A. Okay, always. There is no like A that I could think of where this is not going to be true. For A plus negative A, right? If I did A, B, C, D plus negative A, negative B, negative C, negative D, I will get 0, 0, 0, 0. Okay, for any matrix A, I could find you a negative A. Okay, and you could list anyone you want. I could give you a negative version of that, that's going to work. Okay, number 5. Literally the number 1 times A will be A, right? If I distribute a 1 throughout all the components of A, it won't change anything. If I did C1, C2, A, I would get C1, C2, A, C1, C2, B, C1, C2, C, C1, C2, D. Okay, if I did C1, C2, A like this, I'd have C1, C2, A, C2, B, C2, C, C2, D. And then if I did that last distribution, I would get the same thing, right? And so they're the same. And so you're just kind of verifying that if I do these different things, will something weird happen? Will I see anything, any time where that wouldn't work? And then you could do it for 7 and 8. Okay, just make sure that if I do C times A plus B, I get the same thing as if I do CA plus CB. Okay, and you would just do those two things, make sure that they come out the same. Okay, but you could think of it 3x3 matrices. They're all going to make a vector space as well, or 5x5s, or 2x5s. Okay, the other thing you want to make sure is while you're doing this, none of the answers should come out not a 2x2. Okay, that's part of the point is when I do these things, I just get another 2x2 matrix as well. So like the answer here, these should all be 2x2s. They should be part of the same space. You shouldn't all of a sudden jump into another space. Okay, even functions can be thought of as a vector space. So like literally f of x equals x, f of x equals sine x, f of x equals whatever, cosine x plus x squared plus natural log of x or whatever. Literally, you could just have all functions, real valued functions, and the 8 conditions would be met as well, right? If we went number 1, if I take a function f of x and I add a function g of x, can you think of any real valued function where it would not be the same thing to do g of x plus f of x? No. Okay, those are going to be true. Same idea. Could you think of any time where I took 3 real valued functions and added them in different orders? So let me label these f, g, and h instead of what I just did. So like if I took x plus sine x plus cosine x plus x squared plus natural log of x, would it matter which order I added them in? No. Okay, does there exist a function that acts like 0? Well, sure. 0 is a function, right? And that if I add that function to any other function, nothing changes. Or is there basically an additive inverse of every function? Yes. Okay, for example, negative x plus x will be 0. Negative sine x plus sine x will be 0. Negative cosine x plus x squared plus natural log of x plus cosine x plus x squared plus natural log of x will give you 0. Any real function you give me, I can just negate it, add it, and it will work, right? 5, if I take a number 1 times a function, I will still get that same function. Again, that just being a real number 1. If I take 2 scalars times a function, you're going to get the same thing as if I multiplied one of the scalars times a function, and then the second. If I took a scalar times some function plus another function, I can distribute that scalar to all the functions, right? This is all basic algebra stuff that you guys have had to do for a long time. So with functions, it all works as well, meaning these are technically a vector space. Okay, you could think of functions as vectors, and they will follow the rules that we're going to lay out for vector spaces. Right, hopefully you guys would see this list and say, well, sure, that's all true. I know that's all true. There's no function I can think of. If you can think of any time where one of these rules doesn't meet, that's your counterexample. It's not a vector space, even if it's only one. If I say, oh, no, I know an f of x where this is not true, then you list, that's all you have to do. You don't have to do any of the proof then. You'd say, oh, this means it's not true. Yeah.
So are vector valued functions part of that space, or are they part of a different space?
Vector valued functions would be a different space. Yeah. This would be specifically just like normal real valued functions. But yeah, you could start listing. Again, there's like infinitely many things. Okay. The 0 vector is a space as well. Okay. It's the smallest space. It's the only space with only one vector in it. So literally the 0 vector, the 0 space, 0 vector is a vector space. If we go through 0 plus 0 equals 0 plus 0, 0 plus 0 plus 0 will be 0 plus 0 plus 0 in any order. There is a vector that behaves like the 0 vector, 0. There's a vector that I can add to any vector in that space that will give me 0, because the only vector in my space is 0, and 0 plus 0 is 0. If I start multiplying scalars by 0, I'll get 0. If I add zeros together and then multiply by scalars, I'll get zeros. So the 0 vector is considered a space as well. And it's literally the only space with one vector in it. Okay, dimension refers to the smallest number of vectors needed to describe all other vectors by linear combination. So R2 is 2-dimensional. Well, yeah, because it's called R2, it's easy to think 2-dimensional. Think we can describe every vector in R2 with 2 vectors, some multiple of I plus some multiple of j. Right? That's what it means by the smallest number of vectors you would need to describe all others by linear combination. I and j are not the only choice. They're the simplest choice to describe all of the other vectors, but you could take 1, 2, and 2, 10. Okay, you could take those 2 vectors and you could describe all the other vectors in R2 as multiples of 1, 2, and 2, 10. And I could give, it would not be pretty, but you could do it. There's no reason the axes need to be perpendicular, like we do X and Y. You could choose R2 axes that look like this. Plotting is going to be difficult, okay, and things like that. But we only need 2 vectors to make linear combinations of those 2 to get every other vector in R2. So R3 is the same. Okay, R3 is 3-dimensional, not because it's got a little 3 on it, but because we could take 3 vectors and with linear combinations of those 3 describe all other vectors in R3. Okay, 0 is the only one considered 0-dimensional. Okay, it has only one vector in it. And just think on those properties, every other space has to have a 0 vector. That's one of the properties we need. So you know that it's, if the space consists of other vectors, they can't just be 1 unless that 1 is 0. Okay, if you got other vectors, you're going to have those and the 0 vector in it. Okay, so every other space is at least 1-dimensional, meaning I need one non-zero vector. All right, subspaces is just a shortened way of doing all this. Once I know I'm already part of a space, Okay, so I already know, like, I'm going to take one set of vectors from R3. I don't want all of R3. I want this grouping of R3 vectors that all have this thing in common. Does that also make a space? Okay, that's called a subspace. You're just taking like a little subset of vectors from a known space. Okay, they are spaces by themselves as well, but we don't have to do all 8 conditions. If they're already part of a larger valid space, we need 2 things to be true. That adding them to other vectors in the subspace gives you vectors in the subspace, and multiplying by a scalar will give you vectors in that same subspace. And again, I'll give you some examples in just a second, if this is a little abstract to think about. So you think if you could take not all the vectors in R3, but only certain ones that have certain things in common. And we're trying to determine, like, will they also kind of behave like a space in and of themselves? And the answer is yes, some of them will, as long as when I add any 2 vectors in that subspace, I don't get a vector that's not in there. And as long as I multiply by a constant, I'll also stay in that subspace. Okay, so a good way to picture this, picture a plane going through the origin in R3. So say that's the origin and a plane cuts through it. The vectors in that plane are a subspace of R3. They will have 3 components in them. If I take vectors in this plane, they might be vectors 1, 1, 1 and 1, 2, 3 or whatever that are both in that plane. If we start adding multiples of those vectors together, we'll get other vectors in that plane, right? No matter what, if you start adding those original 2 multiples of them together, you won't all of a sudden get something jutting out of the plane. They'll all be in the plane. If I take constants and multiply by those vectors, it'll just change the length. It will not change the direction. They'll also be in the plane. So that would be a concrete example of a subspace. It's no longer 3-dimensional. It's 2-dimensional. Even though it's a part of R3, it's not all the vectors in R3. It's just vectors on a plane. Okay, a line through the origin would also be a subspace. Okay, if I take vectors on this line and I add them to other vectors on that line, I will get more vectors on that line. If I take that vector on the line and I multiply by a scalar, I'll get other vectors that are also on that line. That would be a 1-dimensional subspace of R3. They must go through the origin, because remember, we need the 0 vector, and the 0 vector is from 0, 0, 0 to 0, 0, 0. So it is the origin. All subspaces must go through the origin. So other planes would not work if I took a plane not through the origin. And this goes back to what we did in the first lesson with expressing planes as a linear combination. And remember, if it didn't go through the origin, we had to add an extra vector on to like shift it. That relates to what we're doing now. You know, it has to go through the origin to be a subspace. Okay, the sum of 2 vectors in the plane will still be in the plane. The scalar product of vectors in the plane will still be in the plane, which is what makes it a subspace. You only have to verify those 2 things. Okay, sometimes these conditions are just combined into one, called the rule for subspaces. So instead of seeing, and these should be vectors, didn't bold them. V plus W is in the subspace and C times V is in the subspace. Those are called closed under addition and scalar multiplication. Sometimes we combine those and just say any linear combination of the 2 vectors will also be in the subspace. So like C times V plus D times W. No matter what I choose for V and W, or what real numbers I choose for C and D, if I do this, I will get another thing in that same space. Okay, lots of words on today, sorry. It's a lot of stuff. Okay, so vectors on the lines through origins are also subspaces. I already said that. So as long as it goes through the origin in 2 dimensions, 3 dimensions, even if you thought of like 5-dimensional if you put a vector on that line and start adding it to other vectors on that line or multiples of other vectors on that line, you'll get more vectors on that line. Okay, it's going to follow a predictable pattern. You won't all of a sudden add it to multiply it by something that's going to get it to do that. Okay, multiplying it's going to get vectors either going that way or vectors going that way. All right, so R3, again, one that we're at least somewhat comfortable with. All possible subspaces of R3, a line through the origin, a plane through the origin. R3 itself is considered a subspace because it does meet those conditions, and the zero vector. There are no other subspaces of R3. It's like a point in R3 won't be a subspace other than at the origin. That point, I guess, could be. Other planes can't be. Other lines can't be. You can't just select like a random region of R3 and say, is this going to be a subspace? It won't be. Okay, the only subspaces in R3 are lines through the origin. There are infinitely many, right? Infinitely many lines or infinitely many planes to choose from, but four main categories: the line through the origin, the plane through the origin, the entire space itself, the zero vector. Okay, in R2, we have basically the same ones, except we can't have other planes, right? In R2, there is only the XY plane. So in R2, you would have these same categories minus the planes. And in R1, you really have one subcategory, which would be the zero vector. Okay, as you go up, you have kind of more options. Okay, so if you were to think about this, and I kind of just told you this couldn't possibly be true, but if we're trying to say, what if we choose only vectors whose components are positive or zero? So like we choose vectors from here. Would those be a subspace of R2? Okay, the answer would be no. Mainly, I just told you that that can't be. But think if you took something in R2 where both x1 and y1 were either positive or zero, would it be closed under addition and subtraction? So say I took two vectors that's components were either positive or non-zero, this one would be fine. This is still in the quadrant, right? I can't add positive and non-zero numbers and not get other positive and zeros and get other positives and zeros. You won't all of a sudden get a vector going like down here. If I add something going here and going here, the result of that will also be in that quadrant. The problem comes from, what if I take a real number times x1, y1? It won't always be in that quadrant. So like all I would need to say, why is it not? -5 times 1, 2 equals -5, -10, which is not in the subspace or in that category or in that grouping, right? If I take 1, 2 and multiply by some scalar, I can get things that will get it to go down here, essentially. All you need is a real number. C itself does not have to be a part of this. C is just any real number. So why is it not? All you need is a counterexample. Either addition doesn't work or multiplication doesn't work. Okay, work meaning stay in that same space. Okay, so what if we included the other space as well? What if we said, okay, well, we'll take stuff from up here and we'll take stuff from down here? Why is that still not a space? Well, I now added in the thing that was causing the trouble. Well, think what would happen. Are there any vectors from up here and down here that I could add together that won't give you more vectors in one of those two quadrants? Well, sure there are. Oh, sorry. It has to either both be positive. vectors are both positive or 0 or both negative. So you could do 1, 2 plus, well, I should have done something farther apart. We'll do 1, 3 plus -2, -2. Okay, 1, 3 is in the first quadrant. -2, -2 is in the third quadrant, but when I add them together, -1, 1 is not in the first or third quadrant. Okay, this is what we'd say not closed under addition. That if I take things from those two quadrants and add them together, I won't always get things in those two quadrants. So we could see that even if we start trying to add things in, what we're eventually going to end up with is that you would need all of it for it to be a subspace there, which means you'd need the whole XY plane. So all you need is if it's not, is one counterexample. Literally, then you can use real numbers and just put numbers and see this one doesn't work. Okay, are all upper triangular matrices, do they make a subspace of M, which we said was any 2 by 2 matrix? So think if we had matrices like this, can you think of any upper triangular matrix that when I add it to another upper triangular matrix, you won't get an upper triangular matrix? No, you're always going to get one, because the only thing that would make it not upper triangular is this, if this all of a sudden became non-zero. But there's nothing you could plug in for any A, B, C, E, F, and G to make this not be upper triangular. It will. Okay, is there any constant? I shouldn't, C is used, so we'll say, no. DA is upper triangular as well. Okay, there's no constant real number I can multiply by A to make it not upper triangular. We'll finish the rest Friday. So you guys have a good afternoon, and I'll see you guys tomorrow for a check-in.
Thank you.
Bye, guys.
Thank you.
Mr. Smith.
Yeah.
I had a question on one of the questions on the problem set.
Okay.
It was 20C.
It was what?
20C.
From problem set 2, I'm guessing? Yeah, obviously.
Yeah. I just like know like how to figure that out.
Find it real quick. Set 2. 20C, is that what you said?
Yeah.